Who'd like a sweetie? Hands up if you'd like a sweetie. I need responses, please. Hands up if you want a sweet, please. One, two, and hands up if you don't want a sweet. Perfect. Okay, so when I arrived, somebody said to me, Jamie, yes, I see you're giving a talk. I said, yes, I am. He said, what's it on? And I said, it's on broadcast. And he said, yeah, okay. Are there going to be sweets? So, yes, there are. This is Tablet, all the way from Scotland. If you don't mind, I'm going to have a bit for myself because I need some sugar. This is a mixture of sugar, milk and butter. I have another packet, so anyone who wants it, please help yourself and pass it round. There you are. Oh God, I needed that. So I'd like to draw your attention to the fact that we just performed a broadcast protocol. I said, do you want sweets? And you put up your hand. That was a broadcast. Hands up who's familiar, please, with decentralized algorithms. Nearly everybody. Okay, so I'll still just briefly remind you, a decentralized algorithm is an algorithm that runs across many participants. So in this example, we had a little round of sweet query, and I was the leader of this round, and I broadcast a message which you all received. And it was synchronous. Effectively, the message arrived instantly. I didn't have to worry about the message getting dropped on the floor halfway to you. Okay? It would be different if we had to communicate by carrier pigeon or by leaving little notes behind park benches. And then messages would take time to arrive, they might get dropped. So there's a whole area, a very difficult area, of designing protocols for broadcast and consensus that make various assumptions about whether messages arrive, how long they take to arrive, whether participants are honest or might be lying. I'm going to report on some consensus research that Isaac Sheff, who can't be here today, and myself have carried out over the past 12 months to understand his ideas on heterogeneous broadcast and consensus. I'll explain what heterogeneous means later. Just out of interest, who thinks they already know what heterogeneous broadcast means? I'll half put my hand up. Am I in frame? I can see myself over there. Perfect. Okay. Just to give you a map. There's going to be two players in this game. Heterogeneous Bracha broadcast. You will see that in this talk. And then there's heterogeneous Paxos, which is a more sophisticated thing that builds on HBB. We're doing HBB in this talk for two reasons. First of all, we haven't built HP yet. And secondly, HBB is small enough to fit into this talk, just so you know. The motivation for this is that Anoma plans to use HBB and HP as their broadcast and consensus algorithms respectively. So there is a reason why these things are being studied. Oh, and as I say here, they don't yet exist. Part of the brief, before we study HBB, we have to invent it. And by the end of this talk, I hope you'll have a flavor of what heterogeneous broadcast and consensus look like and what the issues are involved in creating this. I am here for you. We've all come together. Viewers at home, thank you for logging on. Please do not hesitate to ask questions. Who's monitoring the YouTube channel for online questions? Is there anybody monitoring it? Jonathan, are you volunteering? Thank you. So you are officer in charge of it. I will not see it unless you tell me. So,
yeah, I will raise my hand.
Perfect. Well, yeah, raise it high because I might be absorbed in delivering slides. Thank you. Let's thank Jonathan. Thank you, Jonathan. Terence, did you have a question?
Yeah, does exist mean, does exist in that sentence mean in terms of just...
No, you're supposed to take it from me,
I'm
Terence.
sorry. does exist in that sentence mean in terms of specification even, or just in terms of code?
Oh, in terms of specification.
Okay.
So this is
So
going
even
to...
the subject of this talk is not fully...
Correct. So the brief was first invent HP and then study it.
Okay. Will we have invented it by the end of this talk?
Not HP. You will see half of HBB by the end of this talk.
Okay.
And I'll mention this is the first public announcement showing the first performance of HBB.
Are we under any pressure to invent the rest of it?
Yeah, okay. So there's more than one HBB, and I will show you the crappy simple one.
Excellent.
But even the crappy simple one is better than none at all, which is what we had until about 4 weeks ago. Okay?
Makes sense. Thank you.
Pleasure. But leave it there in case the mood strikes again. Okay. So, broadcast, a little bit of background. Broadcast and consensus protocols, their goal is to help a group of participants, terminology is inconsistent, decide, deliver, output, learn, all of these words are used. A value V proposed by a participant in the presence of some bounded amount of faulty behavior. So let's just try it. Christopher, please, could you announce a number between 1 and 10?
7.
Did you all hear that? There you are, the protocol worked. You didn't hear it. Excellent. You did. Well, no, you might be a faulty process. That's fine, okay? Yeah. And we could spice it up a bit. Suppose that Christopher says the number, but then crashes, and only Terence hears him. So now we'll have the protocol that if you hear the leader, then that's you done. Otherwise, you wait to hear somebody else report what the leader said. Now that works fine, unless there are hostile participants who might just be emitting random numbers, right? So then there are quorum-based approaches. Hands up who knows what a quorum is? Thank you. But I'll just spell it out because it will come up later. A typical example of a quorum is more than half. So if more than half of the people say that Christopher announced 7, and if we assume that there are fewer than half faulty participants, then we can be confident that Christopher did say 7. Make sense? Hands up if that makes sense. Okay, thank you. So here are relevant correctness properties. Agreement. If a correct P, this really annoys me in the literature, nobody defines what correctness means when they state the correctness properties. Correct will mean live, which means responding to messages, and following the protocol. So if a correct P delivers V, and correct P primed delivers V primed, then V equals V primed. Anthony, what number did Christopher announce, please?
9.
We have our first Byzantine participant, thank you. Right? So I am also a correct participant. I also heard 7, so that's working. And Tobias is faulty. Thank you for that. He announced 9. That's fine, right? The algorithm should be able to handle that. Totality for broadcast says if correct P delivers, then every other correct P primed eventually delivers. In particular, this gives you a guarantee. If you are correct and you deliver, then you know that all of your correct friends will also deliver. But in broadcast, it's possible for nobody to deliver, even if they're correct. Consensus is like broadcast, but a bit stricter, that every correct P should eventually deliver. Now, somebody somewhere might be saying, no, hang on a second, that's not possible. What if everybody's crashed? What if the network's down? That's true. So there are implicit assumptions here on how faulty the world is. Right, so for whatever your attacker model is, you've got a valid consensus protocol if all correct processes eventually deliver. Make sense? Just out of interest, to whom is this all completely familiar? Okay, good. Then I'm glad I put this slide in. Thank you. I'll just take this opportunity to thank those who gave me feedback on the slides. Much appreciated. I've acted on all of it. It's been very helpful. Thank you. So we can sum this up as follows. Subject to assumptions on the attack model, for broadcast, correct processes must deliver and agree if any one of them delivers. And for consensus, all correct processes, participants must deliver and agree. I'll move on to the next slide unless there are questions. Okay. So the problem is, before Anoma can use HBB and PHP, somebody has to create them. Now, Isaac had proposed an HP algorithm, and I had developed an axiomatic method for analyzing distributed protocols. We'll see an example of these axioms later. So we decided to apply the proposed axiomatic method to understand the proposed heterogeneous Paxos protocol and see what would happen. What happened was we broke it. The original HP proposal was defective, right? I would like to give kudos and plug the axiomatic method. That's what enabled us to find the error. We also proposed 2 replacement HBB protocols, the cheap and crappy one I will present today. Before we dive into that, because it's a bit difficult, let's motivate homogeneous and heterogeneous broadcast from daily life, okay? So we haven't got to the hard bits of the talk yet. Please consider my family, which consists of mum, dad and son. 3 participants. Now, participants mum and dad use a carefully crafted bespoke communication protocol to deliver decisions in a list to son. Now, I actually once read a manual on child raising when I was a kid, and I remember it said, be consistent in your instructions to the child. It's more important to be consistent than to be right. I mean, if you're wrong, then maybe you should correct it, but if you're inconsistent, there's a unique pain to that, right? Very good advice. I recognize the wisdom of that even when I was, perhaps especially because I was a kid at the time. So this is agreement. If mum and dad announce values vi and vi primed, these should be equal. For example, I should not tell my son that he has to shower before bed. This bears no relation to reality, of course. And my wife says that he doesn't. That just should not happen. Notice an implication of this, that even if my wife believes that my son shouldn't shower before bed, she still has to agree with me if I have announced V first, right? And totality, which is that if mum announces some decision, then dad will back her up. For example, if mum tells son to shower and son prevaricates, then it is expected that dad will eventually get up off the sofa and say, do as your mother says, son, right? We expect this, right? That is totality. And part of the point of this slide, I'm not being frivolous here, this is, it's easy to read these and think, yeah, mathematical safety properties, but this is a real thing, right? So what's heterogeneous broadcast? Well, let's consider a more complex situation. We have mum, dad, grandma, auntie and son. Now, in the instruction manual on child rearing, the author said, don't worry if grandma has different rules. Your child is intelligent enough to know that a different house will have different rules. Don't waste any energy trying to get a single rule set between the households, so long as you're consistent within each place. Wise words. So my son knows when he's visiting grandma's house with his aunt that this pair of adults might occasionally produce different values from what he's used to from his parents. But he knows more than that. He knows that if there is a split, it will split in 2 camps, mum and dad and gran and auntie, right? So, first of all, although there may be differences in the values decided, this is not chaos. Secondly, son has non-trivial, heterogeneous, hierarchical expectations about who will remain in agreement with whom. And when you think about it, that's really important for the stability of his worldview, right? He'd get really confused if the 4 major adults in his life started agreeing and disagreeing one day at a time with one another in random collections. No, there's a stability to it. And in particular, these expectations exist a priori before algorithms are run. It's not that he observes our behavior and then decides whether Auntie is going to agree with Dad today or not. He knows this is how things are going to work out. So this is what heterogeneous means. There might be disagreements, but it doesn't devolve into chaos, and there are predictable zones of agreement, even if, for whatever reason, some disagreement might arise. Hands up if that makes sense, please. Okay, thank you. So this is the game we're trying to play. Intuitively, heterogeneous means the universe might split into factions which will agree with themselves. This splitting might be the result of faulty behavior, Byzantine processes, but it might also be inherent to what we're considering. For example, if we're bridging between blockchains, we might not want the two blockchains to agree all the time. Participants don't know in advance who will be faulty. That would defeat the purpose of being faulty. They have to deduce it from behavior. But the trick is to predict areas of agreement against all possible faulty behavior subject to certain assumptions, like no more than 1/3 of the universe is faulty or something like that. Okay. Can I move on to the next slide? Wonderful, thank you. Right, well, let's get to it. Does everyone have tablet who wants tablet? Hands up if you want tablet. I do. Thank you. Lecturing runs on sugar. Whoops. Oh well, there we are. Thank you. So, let's annotate participants with a follows relation. If we expect it to be symmetric, which is the case in the informal examples, we might call this relation should agree. So in the previous example, son expects dad and mum to agree and gran and auntie to agree with near certainty, and usually mum may agree with gran, but not always. So how we generalize, before we even design the protocol, let's decide what the correctness properties should be. Well, agreement is if P delivers V and P prime delivers V prime, and P prime follows P, then the value should be equal. Right? Hopefully this now seems like completely obvious. I mean, yes, obviously, what would you expect, right? And totality is that if P delivers and P primed follows P, then eventually P primed should deliver. All if correct, obviously. We can't control faulty participants. By definition, they don't follow necessarily follow the protocol. Now, I just want to hammer home the point that this follows and should agree relation can be non-trivial. Now, I noted that before with the mum and gran example, but let's take another example. Supposing I follow Isaac and Isaac follows Christopher, and I learn that hackers have used AI to steal Christopher's identity and clone his likeness. This is a real thing nowadays, unfortunately. It could happen. Perhaps we should have a protocol in place, like secret code words or something. I tried to do that with my family, but they forgot the code word. I gave them a whole speech about the important. They didn't even remember. So, now I know that Christopher's been faked, I can't trust him. Not because I don't trust the real Christopher, but because I don't know who I'm communicating with. So, you know, any messages from Christopher, I have to ignore them. But supposing I also suspect that Isaac doesn't know that the hackers have faked Christopher, maybe Isaac is still following Christopher. So even though the hackers haven't cloned Isaac, I can't follow him either, because any information that comes from him might have been corrupted by the fake Christopher, which Isaac is following. So I want you to note a subtlety that's embedded in this notion of following. It's about, not just about what is, it's not even just about what I know, it's about what I know other people know. Right, I'm just going to put my head under the table here like this for a second. Yeah, this is really happening, right? Terence, you have a question?
Yeah.
You need the mic.
Oh, thank you. So is this following relation, then, is this subjective, as in something that I specify, or is that itself subject to consensus?
It's not subjective, it's epistemic. It's about knowledge. So I illustrate here, I can't follow Isaac because I don't know whether Isaac is following Christopher.
So this notion of knowing will be represented in protocol?
Exactly. This is the question. This is why I was just under the table with my hands over my head, right? Because there's a lot going on here now.
Yes.
So you're right to be suspicious, and basically the past 12 months of my life have been an absolute hell or delight, depending on your point of view, trying to straighten this out, right? For a start, trying to understand what's going on, and then how to represent it. Do not worry, you will definitely see the mathematical model of that in this talk.
Thank you.
Okay. So, just to sum this up, before I get to the maths, there's some pretty serious stuff going on here under the hood. And it's all kind of pulled out of this question, oh yes, please design heterogeneous Paxos, please. Right. And I'll indulge myself in saying that the concepts were not delivered to me in this form. We had to figure it out, right? And I say we, because Isaac and I were working together on this. We had many long conversations, and what we've come up with is presented next. So, we won't need much to formalize this. We'll just need semi-topology, historical structures, and modal logic. Hands up who's familiar with modal logic? Nice. History structures? I'm surprised because I just invented them.
Oh.
But thank you. Thank you. I'm going to do a full check on my 2FA.
I assumed you meant something like a snapshotting file system.
Something else. This is the thing that you wanted, the epistemic model, the model of knowledge. That's history structures. And semi-topology, who's heard of semi-topology? Okay, don't worry. A semi-topology, aka a quorum system, is, I'll just say, now we come to the maths bit. Please interrupt me if you get lost, right? There's a lot about to happen. Is a set of participants and open sets, which I may call quorums. Yes, Jonathan.
Is your wife on the chat just saying, I hope you all enjoy the tablets on the top.
Hope you enjoy the
Tablets, the candies.
oh, the tablets. Thank you very much. Thank you for being here online. Hi. So think of open sets as quorums. And typically, you may have seen this, that we take open sets to be supermajorities, strictly more than 2/3 of participants. That's the standard thing. So if you haven't heard of semi-topologies, just imagine it's one of these quorum systems, and nothing bad will happen to you, right? Christoph, you'll need the mic.
I'm getting out of my depth here, but are we assuming a predetermined number of participants, or is
Yes.
the network dynamic? Okay.
So for this simple model, P is fixed and open is fixed.
Okay.
This will be made formal later. There'll be a notion of model which we fix, and then we run the algorithm in that model. That's it. Thank you. Great question. Any more questions? Okay. Now, the only thing I need from the theory of semi-topologies is a notion of a neighborhood system. So I will now use the board. If we have a participant P, then neighborhoods of P are just quorums, open sets that contain P. That's all. Okay? So please hold on to that thought. I may call O a quorum of P when it contains P. That's it. Okay? So whenever you see neighborhood of P, it's a set of open sets that contain P. As discussed, following is inherently epistemic, which is a fancy way of saying that its validity depends on what P and P primed know about each other in the universe. So here's some examples. It's raining is not an epistemic statement. Its validity depends on whether it is raining. And mostly, we believe that either it is raining or it isn't, even if we don't know. So that's a modal statement because it depends on where you are, but it's not an epistemic statement. It does depend on what you know about where you are. However, Terence, I trust you. That is epistemic. It depends on what I think I know about your behavior, depends on what I think I know about your character, but it also depends on what I think I know about the people who might influence you, right? So there's a phrase which doesn't apply to you, nice boy but easily led. Right? To be clear. Does not apply to you. But that's a nice illustration. It's that this person may be of good character, but they hang out and are susceptible to influence by untrustworthy actors, and therefore we cannot trust them as well. So that gives an example of the detail in following, and thus in the word heterogeneous. Okay, now we're really going to hit the maths. We fix disjoint sets of participants. This P is the same as that P. How am I doing for time, Christopher?
All right.
Yeah, how much have I got left? Please. And events. And we define prehistory to be, a prehistory is a finite set of tuples of a participant, an event, and another prehistory.
20.
Thank you. So let's suppose we have participant P declares event E, and then there's a prehistory H, and that H is a tree of more of these things. P prime declares E primed in H primed, and P double primed, and so on. Does that make sense? Tobias.
Yeah, there's an obvious duplication of the word prehistory left to the equation sign, and on the right.
It's an inductive definition.
It's an inductive
Yeah,
definition.
so prehistory is the least set.
Right.
Sorry, I should have said that. Apologies.
So basically, the base case is like an empty set.
Yes, perfect.
Okay.
And we
Great,
build
so-
it up finitely.
Great, thanks.
Thank you. Great question. So we can easily build prehistories just by starting from the empty set and then just building upwards inductively. And if you've done any set theory at all, you'd have seen these kinds of trees, right? Models of set theory. Well, prehistories are exactly the same, just turned upside down, and stuff's labeled with a participant and an event. So I'm a participant, and the event is I say, who wants tablet? That's a broadcast event, right? Prehistories aren't quite what we need. We need prehistories that are transitive, which is this thing here. It says that if H primed appears somewhere in this triangle, thank you. If H primed appears somewhere in this triangle, then it's also an element of H. It's a subset, yeah. So any history that, the notation's a bit unfortunate. If some H primed PE H primed tuple appears in H, then H primed is already a subset of H. Right. Again, if you've done any set theory, you will recognize this. This is basically an elaboration of the von Neumann ordinals. I promised you set theory, Terence. There it is.
Right. So first of all,
Microphone, Terence.
sorry. So prehistory is a well-founded tree labeled by pairs P event, right?
Yes.
Finitely branching.
Yes.
Right.
Correct.
Right. Okay. Which is, yeah, it's the right.
You can look at it as trees. It might be more useful to think of it as sets that are coloured by these labels, a pair of P and E. Right. So every that's how I think of it. And then you have this transitivity. I don't want to get too hung up on this
Right.
thing.
They do have that annotation, but they also have paths, right? They're richer.
Yes,
than,
correct.
They're richer than just labels. Right. S expressions with labeled by P event.
Thank you.
Thank you. Okay.
Okay, unless there are other questions? Okay.
Could I take another look at the subset notion?
You absolutely can. Arthur, you had a question?
Yeah. So what we're assuming is that the prehistory is like strictly ordered. That there's no ambiguity about the ordering of.
I didn't impose an ordering on them. They're, just as Terence said, they're trees. Well, I don't think of them as trees, I think of them as sets. So a prehistory is a finite set of prehistories labelled by participants and events.
Okay.
That's all. Yeah. Okay, while Terence reboots, I will continue. Terence, you need to either photograph the slide or... Okay, I'm going to carry on. Call a tuple. Fine. There. What are you looking at, Terence?
Oh, I was just parsing the in H, since as you were saying, you look at them as sets. I come from a world in which we look at them as trees, right? So I don't necessarily precisely say as element of a tree, right?
But they are
like
sets because this is finite power set, so it actually is a set. I'm going to have to move on.
Yes, go ahead.
Call a tuple of a model where H is a history and P open is a semi-topology. Sorry, call a tuple M a model when H is a... yeah, whatever. Okay. I want to introduce you to one more concept, I'm afraid. Logical time. So, in the literature, protocols are presented in algorithmic time. They're described as a machine that performs steps. I see. So I can't click on this, unfortunately. I should have tested this. But this link here will take you to a paper where there's a presentation of broadcast or Paxos, I don't remember. It's written, it looks like code. It says, if you've done this, then do that. If you haven't seen a message, then echo. And hands up if you have an idea of the kind of thing. Yeah, okay. Christopher is nodding vigorously. Logical time abstracts away from algorithmic time. There's no abstract machine doing stuff anymore. There's just some notion of what logical stage the algorithm has arrived at. In Paxos, that's the round. So logical time is just a number n. In Bracha broadcast, there's no notion of logical time. There are just predicates. I don't have the algorithmic time to go into that in more detail. And I can't show you this because it's not clickable. But I will say that the relevant notion of logical time in HBB is this notion of history. And although I've presented it to you as just slide 13 in the middle of a slide deck, this is a significant step. It took about 8-9 months to get to this stage, to understand that this is a relevant notion of logical time for HBB. And I want you to notice that this is complicated. Paxos, which is already a complicated algorithm, has a very simple notion of logical time, just a round number. But here, because of this epistemic content, a history is basically a set, like you might find in set theory. It's a non-trivial structure. So this tells us something about how subtle these concepts are. I'm not trying to scare you off, I'm just making an observation. Now, we'll need a logic for talking about these things. Terence.
The thing that puzzles me about the set interpretation is that you could have the same set of pairs of P event that do not form that can be arranged into two different prehistories, right? By arranging them in different tree structures.
Did you say PE?
Yes.
Because it's PEH. So a history doesn't just consist of tuples P and E, it's PE
right.
and a prehistory.
Yes.
Yeah. So if you change the arrangement or if you change these prehistories, you will get a different set.
Okay. I think I finally understand what you mean by set. Okay, thank you.
Pleasure.
So the hereditarily transitive prehistories, and that amounts to a path through a tree, right? If I do view them.
Are you familiar with the von Neumann ordinals?
Not anymore.
Well, they have this feature. 4 is an element of 5, and therefore 4 is also a subset of 5, so it contains 3, 2, and 1.
Oh, is this different from Cantor's construction?
It is, I believe, yes.
Okay.
But we're way off topic here, so I will
Yeah.
snap back.
Okay.
So, predicates. This is usual predicate logic, implies for all. This is an event, which is a predicate, well, a proposition. ITP phi says in the past phi. Diamond phi, I'll read that as somewhere phi. This says there exists a quorum intersection on which phi. This says is sequential, and this says p follows p primed. God help us. Anyone want to? Yeah. Yes.
Is diamond someone or somewhere? Because you said somewhere.
Both.
Okay.
Yeah.
Nice.
Someone, somewhere. Yeah, because this is a modal logic, so there are participants. Participants of the notion of place. Good question, thank you. We interpret validity of predicates with respect to a model and a participant and a logical time. So the validity judgment has this form. Phi is valid in model M at place P and time, logical time H. Now the logical time H is what P knows, and M is the universe in which P exists. So M is the whole run of the algorithm. P doesn't have access to all of M, but it does have a fragment of M which is H, and that is what P knows about events so far. So when I said, does anyone want tablet, that was an event that happened. It was a broadcast event by this participant, and I know something about the world when I said that. So that's what we in fact will that's this thing here. So E is valid in PHM when PEH, oh, that mathcal H should be an M. Sorry, that's in a legacy notation. Does this line make sense at least? I know this is a lot. Hands up if this line makes sense, please. All right, yeah.
Can you read it again?
Yeah, so
In your words.
Jonathan has asked me to read this again. E is valid at PHM when PEH is in M. So PEH being in M means that P broadcast E at a logical time, which means when it knows H. So if I say, do you want some tablet? And then you say yes, then you know something. You know that I asked, do you want some tablet? So that tuple, Jamie, offered tablet, H, is in your history when Jonathan, yes, H primed is valid. H primed will contain Jamie, tablet, H. Does that make sense? Wonderful, thank you. Terence, still need the mic again?
I'm looking at the ITP predicate and trying to make sure that I understand this. So if I'm reading the
Well,
order...
hang on. My talk, please permit me to present. I will get to ITP, I promise.
Oh, okay.
I've only done this line.
Okay.
You're only allowed to ask questions about stuff that I have already confused you about, not about this. I haven't had the opportunity to confuse you about it yet. Okay, we'll get there. So let's just do this one. Phi implies phi primed when phi implies phi primed at PHM. Hands up if that makes sense. Perfect, thank you. And hopefully for all p prime phi is also intuitive. Note that, I'm not sure I meant to do that. No, that's a typo. That should be p. I apologize. This is just quantification over all other participants. So that prime should not be there. Okay, in the past phi says that, well, what is the past? The past is H, because H is what P knows. It's P's logical time. So in the past phi is true at PH when in some past time in H, pH primed was valid. Tobias wants a mic.
So at this point, I wonder, like, is this... Well, at this point, I remember that you said that the histories have to be transitive.
Yes.
Now I wonder, like, what if we drop that requirement and change this line to, on the right-hand side, there's
a
H prime.
chain of...
No. Hear me out.
Sorry.
There's H prime in H such that either it is the case as written or in the past of H.
We could do that.
We could do that. So
Absolutely.
that's the only line that connects to the
You're
transcript.
absolutely right. I could have saved us from histories by changing that line. Thank you. Yes. Terence, do you still have a question on that line?
I was going to try to confirm that I understood then that effectively as we descend a tree, we're moving into the past, right?
Yes,
That
correct.
The subnode of a particular node is in the past of this.
With respect,
parent
yes,
node,
that's
yeah.
right. That's why it's called H, because it's history, but it's P's version of history at H. You may remember I was talking about modalities and places. Well, the notion of place for a model M is a pair of P and H. That's whereas E is not a place, it's a thing that's either true or false at a place. And then somewhere phi is just true when in the same history we can find some P primed that has phi. 10 minutes, thank you. I'm not doing too badly. Yes.
This is very special relativistic, right, in the sense that there are incomparable times, right? There
Are
histories
indeed
that are
incomparable times, and we're going to
neither
come
which
to
is in
that
the past
actually.
or the other. Yeah,
Yes.
okay.
Good, thank you. Now, frankly, it's unreasonable of me to show this to you, but, what the hell. So this box takes a bunch of participants, L1 up to Ln. It finds an open neighborhood, a quorum of each one of them. So it might pick O double primed for P and some other thing for L2 or whatever. And then it takes their quorum intersection and checks whether phi is true on that entire quorum intersection. So if there are two learners, sorry, I called them learners by accident, they're just participants. If there are two participants, then box.L primed would mean that there's a pair of open sets and their intersection has phi, which in this case is being read. Hands up if that makes sense, please. Thank you. And the useful special case is when there's just one participant, in which case box.phi means there exists a quorum that has phi. Now, you may be familiar with this from consensus protocols where they say, if you see a quorum of such and such, then you should perform some action. Well, this is a predicate that checks that. May I carry on? This has a De Morgan dual. After this, things will get easier, by the way. The De Morgan dual is just not box dot, not phi. And if you unpack what that means, well, box dot was there exists opens such that all of their intersection has phi. This says for all opens, some of their intersection has phi, which is the dual. Okay. Thank you for staying with me thus far. Oh, and I forgot sequentiality. It gets easier after this slide. But this is actually really pretty. Check this out. I'll say that P is sequential at logical time H when for all events that happened in its past, either in the past E and in that past E primed, or in the past E primed and in that past E. So this is an echo of algorithmic time. In the real world, participants do stuff one step at a time, right? I might offer you tablet and then offer you, I don't know, water, right? Or I might offer you water and then offer you tablet. And we know, me being a correct participant, I must have done one before the other. Now, why would we want this? Well, in the real world, events are cryptographically signed by whoever did them. So a hostile participant can't just make shit up. You can't say that I offered you falafel if I actually offered you tablet, because you can't fake the cryptographic signature on my event. But what you can do is omit critical details, right? And context is everything. If you see me running out of a shop with a handbag, am I shoplifting? Or am I running to catch a lady who left it behind, right? So this context is important, and this is how we detect hostile participants. The only way to be hostile in the system is to omit stuff from your history, right? So sequentiality is the mark of an honest participant. I can tell I'm running out of time, so I'll just skip over a whole bunch of stuff. This is the HBB protocol. Never before seen. It's expressed in axiomatic style. Let's look at this. Supposing we echo 0v, this is an event. That implies that in the past, somebody must have proposed v. Hands up if that makes sense. Great, thank you. Supposing we echo 1 LV, that means that in the past, that there is an L quorum of past echo 0 Vs. Algorithmically, this would be written as, if you observe a quorum of echo Vs, then echo 1. Yeah? And this would be written as, if you observe a propose, then echo 0. But in this logical style, we go backwards. If you echo 0, it must be because in your past, you knew about somebody proposing. Now, I don't have time to go through, well, let's just go through the vote. If we vote L prime V, that means that if L is following L primed at this time, and in the past, somebody echo 1 L primed V. In a way, it almost doesn't matter what the details are. I just want you to see that we're using this logic. I'm really sorry that there's so much stuff that we had to wade through to get to this slide, okay? In a way, this slide is a distraction. What's relevant is the notion of history structure and the predicate logic. Once you have that, you can write down these algorithms on 5 lines and you can experiment with them and start proving stuff, right? So that's where all the action has been. And I'll just ask you to take my word for it, unless you want to give me an extra 5 minutes, which I'm fine with not having. There's a little lemma that shows that correctness, agreement, if 2 participants deliver, then they deliver the same value. And there's a proof that does some stuff. And all I want you to note about this is, it's all within the logic now. We have, everything is precise. There's no hand waving or talking. We're just manipulating a well-defined mathematical structure to get a mathematical result. Any questions on that? Okay, so what have we learned? This is hard. There are lots of definitions. Finding them was not obvious. It's taken months to get there, and I've exhausted an hour just setting this thing up. Okay? Please excuse me for that. On the other hand, once this is set up, the axioms expressing the protocol are straightforward. And the end result is pretty good. This is a thing. This is a proof. It's either true or false. Happens to be true. Great, we're done. There's a large design space of possible protocols. We've only found 2 that work. Our algorithm has been exhaustive search. I haven't found any systematic way to explore the design space. This isn't specific to me and Isaac. So far as I can tell, people are coming up with algorithms just by being really clever. and thinking of stuff, right? Which kind of offends me, right? It shouldn't be that way. We should write down our correctness desired correctness properties and then derive the protocols from them. That's civilized, but it just doesn't work that way. Fine. I will say that although I have asked much of you in this talk, you meaning one, you get used to this world of histories and these definitions of sequentiality and safe participants. There's a lot of stuff to load into your brain, but then you read it, you do a few proofs, and in retrospect it almost seems obvious. Of course history structures are going to be hereditarily transitive, PE labelled finite sets. Yeah, obviously, right? As a conceptual structure, this strikes me as a solid foundation for future work. I will also say that the logical approach was, for me, absolutely essential to understand the protocol. I couldn't have understood HBB or HP without thinking about protocols in this logical form. And I'll just spell out, I will say the unsaid bit. If you want to do this too, just ask and I'll be happy to help, right? This stuff works. It broke HP. It broke the original HP, right? That's a good thing. Future work, to write this up. There's clearly a meaty journal paper in this. To implement it, it would be wonderful to have a model checker for history structures. Because right now, if I can't tweak a axiom, I have to rerun all the proofs by hand. This is exhausting. It would be so much nicer to plug this into a model checker and ask it to tell me whether it has a counterexample for correctness properties, right? I'd also like to find better protocols. I've shown you a cheap, crappy protocol. There's also a much, I won't say better, it has different properties, but you pay a heavy price in complexity. It's quite long, there's a lot of rounds. And we don't really understand if there's anything else out there. Have we found the two canonical points in the design space? I've wasted many hours that I could have spent watching TV or playing with my son, staring at little quorum systems and trying to devise protocols that don't work. Right? So it would be nice to find something better. And that concludes my talk. Thank you very much.
All right. Thank you so much, Jamie, for that lovely exposition for the first time ever, world exclusive on Heterogeneous Bracha broadcast. We have time for one short question from the audience, if there are any further ones.
Behind you.
Thanks. Yeah, thanks for the great talk. So what would you say, like, when you say it's necessary for exploring HBB for the history structures versus going with the algorithmic approach? Is it mostly about distinguishing between sequential and non-sequential participants?
So the problem with the algorithmic approach, I'm just going to say it here, the algorithmic approach forces you to embed everything into algorithmic time. You have to think about a program actually executing something imperatively. Now I have 2 points here. Who here knows about functional programming? Right. Do you think about stuff executing in imperative sequential time when you're functionally programming? Well, kind of, but it's optional, right? That's point number one. So this axiomatic approach is declarative. It is to imperative programming, it is to algorithmic time as functional programming is supposed to be to imperative programming, right? That's point number one. Point number two, it's just not necessary. This is a claim that I'm making. It's in bad taste. It's wrong, right? The reason things are like that is because the people who invented distributed systems designed algorithms. They weren't functional programmers or... So they had a particular mindset. But that's not what the algorithms are, right? The essential nature of Bracha, Broadcast and Paxos is not to be run on a little machine. You see that because people say for every correct process, if it has not already seen a quorum of n+1 round messages at round n, then it does. is nonsense, right? The essential nature of these algorithms. So I'm making two claims. First of all, yeah, program at the highest level you possibly can, sure. But I'm also making the claim that the essential truth of the algorithm is not in algorithmic time. It's in an appropriate notion of logical time. That is my answer to your question. Thank you for asking.
All right, let's give it up again for Jamie.